Hello students, welcome to this lecture, and in this lecture we are going to study about area enclosed by a graph from some x coordinate to another x coordinate with respect to x axis basically, and we will also see the correlation between definite integration and indefinite integration. Before doing this portion, I would like to also give you the answer of the homework which was given to you in the previous lecture. That was about the moment of inertia of a rod about an axis which is passing through the perpendicular bisector of the rod. That was basically our question, and if you remember, we did it from some other axis also in the previous class. So if I take a uniform rod whose mass is uniformly distributed and I take an axis like this, then the moment of inertia, which is basically given as di is equal to dm into x square, where x is the distance of this small mass from the axis of reference basically, and we want to find the moment of inertia of this whole rod from this axis. So basically, if we integrate this, which we get as I, and we also integrate this portion simultaneously. So first thing that we already studied, that this dm is by unitary method m by l dx. That is, the mass is uniformly distributed, the rod is having a mass capital M, and the length of the rod is actually L. So basically dm is m by l dx into x square. Now the limit portion, which is very important here, which we want to
definite integral part is here.
So if we see here that dx, which is the variable of integration, so it is this direction also and in this direction also. So in normal maths, when you study number system in class 8, 9, 10, you study that on a number line, this is origin, here there is a positive axis, here there is a negative axis. So you can say that from this axis, this is at a distance minus L by 2 and this is L by 2. So you are covering the whole rod from minus L by 2 to L by 2 basically. So this will become m by L, and integral of this is x cube upon 3, which is from minus L by 2 to L by 2, and when you will substitute the values, and we all know, we'll put the upper limit and the lower limit, the final answer which will come out to be m L square by 12. Well, this small portion I think we can leave to students. They will
definitely
do this
part.
part.
Already solved this question also, I hope. And now you can verify that in the last class we have discussed the moment of inertia about this axis, that is axis passing through an end. So the value comes out to be ml square by 3. And this was the point I was emphasizing in the last class, that the moment of inertia depends on the axis, and about this axis it is ml square by 3, about this axis the value is ml square by 12, and definite integral will make our life very easier when we are dealing with those things which can be calculated only using the method of integration.
So the moment of inertia about this axis is less, and about this is more.
It is a general thing that moment of inertia of any body about an axis passing through its center of mass, this is a center of mass that we will discuss in the later class, is always the minimum about any other axis.
Okay, so if I want to rotate like this, it is easiest
to rotate about center of mass than about any other axis.
And here it is little difficult to rotate.
Comparatively, it requires more amount of force
because inertia is more
here.
Okay, so now I would like to come to this topic, area under the curve. So basically, I would take an example which will make you more comprehensible about the concept of area under the curve. So if I take a function fx is equal to 2x, and I tell you to do a question that you have to find the value of f3, okay, when fx is actually integral of small fx. Okay, and it is further given, this is capital F and this is a small f, that you can easily understand here by seeing them, and this integral is a function, and you have to find that value at x is equal to 3 when it is given that fx passes through a point 1, 3. So there are two ways in which one can understand this question, do it. So firstly, if I would try to do it by indefinite integration, so there is a function fx and I am integrating it, okay. So we are getting a capital Fx on this, which will give you x square plus a constant of integration. Now since it is already given that the function is passing through 1, 3, so I think we can get the constant of
So 1,
integration.
3 means value of x is 1 and fx is 3, capital Fx is 3.
Yeah.
Okay.
So capital Fx is actually 3 and x is actually 1.
Okay.
This is the point through which this function is passing. So we can find c over here, which is actually 3 and 1 square is 1. So 3 minus 1, 2. So the exact curve which is coming out to be is fx is equal to x square plus 2. This is the exact indefinite integration of this function 2x.
So just by knowing this fact that the curve is passing through 1, 3, out of the family of curve, we can select a particular curve that satisfies this condition.
Correct. So all the family of curves which we were seeing from this various values of c, the curve is this one, which is x square plus 2. As we
All
also-
these are represented by the same equation, but the value 2 is the difference between any other curve and this curve.
Yes.
This is our curve in this
This
case.
is our curve, and further we are saying find the value of f3.
F3, okay.
So if I come to f3, so it will be 3 square plus 2, which is 11. So geometrically, you can see that there may be a point this on this curve, which is passing through 1, 3. This point is 1, 3, and for some other x, which is now 3, you are getting the y coordinate as 11.
3 and 11.
3 and 11. So this curve is a curve which is passing through 1, 3 as well as 3, 11, and this is the integral of this function.
Given function.
This given function. Now I want to tell you, if I want to find the same thing with definite integration, so it is highly related to the concept of area. There we geometrically we may not need to find this curve. We have to do simply one thing. We will draw the graph of 2x here, and the graph of 2x we all know is a line passing through origin, and it is making an
And with
angle
a slope of tan inverse 2.
tan inverse 2. So basically this is a line y is equal to 2x. Now if I want to tell you about the fundamental theorem of calculus, so if you remember that a function fx dx from a to b is actually fb minus fa. So here this capital F is the integral of
the
this function, and one small thing which I want to remind you that this function is continuous
Yes.
between
In this closed region
this
A,
close
B.
AB. So it is quite obvious it is continuous here. So what does this represent actually? I want to tell you that this FB minus FA actually represent the area from A to B by this function with the x-axis. So this is the function fx, and the interval which I am taking here is x is equal to 1 to x is equal to 3. So initially one x coordinate was 1, and then I took another x coordinate as 3, which was finding the value of this function. So if I will take this portion, so my emphasis on this lecture is all about the area. So this is the area which you will find FB minus FA, and which is represented geometrically like this. So here you have to draw the graph of a small fx, and you will get the area enclosed, which is FB minus FA actually. Now if you want to see here that the area of this portion, which is a trapezium, and I think we all know the area of the trapezium, which is basically half into sum of the parallel sides. So this height plus this height. So this height is actually, if you take x is equal to 1 here, this height is 2, and if you take x is equal to 3 here, this height is 6. So sum of the parallel sides 2 plus 6 into the distance between the parallel sides, which is 2, which is 3 minus 1, 2. So this will cancel 8 square units. This is the area enclosed
by this given curve.
by this given curve. Y is equal to 2x from 1 to 3 with the x-axis. So this 8 square units is also the integration of this function from a to b. So you can easily verify this portion by seeing here, because you have already integrated this and you have seen this is the function, and you have also seen that when you put the limit, above limit and lower limit, so upper limit is 3, you are putting f3, and lower limit is a, which is actually 1 here. This is a, this is b, so f1. So you put 1 here, you will get 3. So what is fb minus fa? So if you see fb minus fa, which is actually f3 minus f1, which is actually 11 minus 3, which is 8 square units, which is the same which is coming out as the area. So definite integration is actually the area enclosed by the function, which is giving you the same value if you integrate it and put the limits, lower limit and upper limit, in the integral part.
Okay.
So basically you can also see the difference between the y coordinates of this point is actually the area.
Okay.
So difference between the y coordinates of the integral and the area of the function. So there is two functions. One is the function itself, another is its integral. So geometrically this is a line, this is a curve, and this line encloses an area, and its integral give you the difference of the y coordinate, which is actually given as area over there. So basically many other things are also associated with this if you try to understand why the difference of y coordinate is coming as area. So dimensionally also it is correct, because what does we do in integration? We integrate the function with a variable. So here there is meter, the length, and dx is also meter, the length. So this function is meter square, that is the area. So the difference of y coordinate is meter square, and here the area is meter square. So basically this we have to understand here, and the next lecture will be basically on area under the
application of the. Now we have already learned application of differentiation, indefinite integration and definite integration. There are some cases in which if we apply the method that you have learned in this class, that is how to calculate area under a given curve. So by applying this method, there are various cases in which the calculation become even simpler, and just by appreciating the fact that area under the curve is the integration from a given limit, lower limit to the upper limit, we can calculate various quantity, whether it is mechanics or heat and thermodynamics or wave. We can apply it everywhere, and the things by applying this become very simpler, and it help you understand and appreciate the lot of concept of physics. So for this lecture, it is goodbye from Subbu sir and Pawan sir. In the next lecture, we will have some more interesting concept of math.